going to be the distance between two parallel planes. All right. So the problem will be very similar to what we did last time. Um, but in this case, rather than finding, pointing a plane is going to be between two parallel planes. Well, number one, how do we know two planes are parallel? Well, we're given two planes right here. So all we need to do is observe the coefficients of x, y, and z, because again, those coefficients give us the direction vector of the plane, the vector that is normal to the plane. So, and in this case, we can see 3, 1, negative 4, 3, 1, negative 4. All the changes is these numbers right there, right? The constant terms. It's just like when you have something like y equals to 3x plus 5 and y equals to 3x plus 1, for instance. So these two, those are from yesterday. So yeah, okay. So this means, well, coming back to algebra, when you had these two equations of line, they ask you to determine whether they are parallel, perpendicular, or neither. So in this case, two lines are parallel when they have the same slope, right? That is the same coefficient of x. And they're parallel, that's also because all they differ by is the number, the constant term, which is the y-intercept. So yeah, they're made in parallel. So in a similar way, we're going to have the same coefficients for x, for y, and for z, and just different constant terms. All right? Well, that's not the only case where planes can be parallel. What if I have 9x plus 3y minus 12 z equals to 11. Is this plane right here, the question I just wrote, is this plane parallel to this plane? How do we know it's parallel? Right, so it's the same coefficient just multiplied by a constant number. In this case, they're multiplied by 3, right? But what about this plane? Say 6x plus 2y minus 6z equals to 13, for instance. Is this plane parallel to that plane? It almost were, right? It almost is, because 6 and 2, well, these 6 and 2 are multiples of 3 and 1. But the one that makes it not parallel, well, it's this negative 6. I should have had, what would make it a parallel plane? Negative 8, right? So negative 8. Okay, so negative 8 would make it a parallel plane. Well, I'm going to erase this. I don't need this. I'm going to erase this as well. And okay. So essentially, we will repeat the process for finding the distance between a point and a plane. How is that going to work? Well, number one, let me draw the two planes. So, I mean, a rough sketch, not like exactly the planes, right? So, because they're parallel, they're supposed to look like this, okay? So number one, we will need to find 2 points, 1 point on each plane, because right here, again, this distance right here, let me call that distance, we call that D, for instance, okay? So, and because these planes are parallel, well, the distance between the two planes it's going to be the same, unless we had land, or rather intersecting planes. Well, the distance changes at every single point. So no, they're no longer parallel. So that means I need a point. Let me call point P on the first plane. Yes, on the first plane, and point Q on the second plane. So we will define that vector PQ that goes from point P to point Q. Again, for also the plane has a normal vector that forms a 90-degree angle with the plane, but actually in this case it's the same normal vector. And again, The shadow of the green vector, that is, this shadow right here, will be exactly the distance between the two planes in a similar way we did it last time, right? But this time, instead of having one single point in the middle of nowhere, it's a point on the second given plane. So I'm going to suppose this is the plane given by 3x plus y minus 4, z equals to 10, and 3x plus y minus 4, z equals to 2. So in this case, we will need to find a point on each of the planes. And again, one way, the hard way, is to find three integers such that 3 times the first one plus the second one minus 4 times the third one equals 2. You want to do it that way? Not really, right? I mean, it's doable, but it's going to take you forever. So what is an alternative to make this easier and quicker? An intercept, right? So let's pick about the equations, right? So, well, what intercept do you think is the easiest for the plane at the top? The y-intercept, right? So using the y-intercept, that'll be y equals to 10. That means the point 0, 10, 0. All right? So that's going to be our point Q. What intercept would be better for the second plane, for the plane below? Y. The y-intercept as well, right? Yep. And now again the y-intercept. Y-intercept, that'll be y equals to 2. All right? And again, here 0, 2, 0. Right? So let's just repeat the process for the plane, for the exercise we did at the end of the class last time. So, okay, number one. So let's define the vector PQ. That is terminal minus initial. That is 0 minus 0. That's 0. 2 minus 10. That is negative 10. 0 minus 0. Minus negative 8. Right? And 0. All right? Actually, you can do it the other way around. You can do 10 minus 2 and get a positive 8. It doesn't matter because for the numerator or for the formula that we're going to find the distance, we are required to take the absolute value because it's a distance, right? So there is no negative distances. So that's the vector that defines the points PQ, that define the vector whose shadow will be equal to the distance, the shadow onto the the normal vector. Okay. So what else do we need? We need to define that normal vector, right? Where do we get the components of that vector? From the coefficients of the plane. And guys, in the case that you get two planes that have whose one of the planes has coefficients that is a multiple of the other, it doesn't matter which one do you use. It's going in the same direction. It's just going to have a different magnitude. So it doesn't matter. Okay? So, in this case, it's the same. That is 3, 1, negative 4. We need the dot product. PQ dotted with N. So 0, negative 8, 0, 3, 1, negative 4. Okay? All right, so yes.
When you draw those two vectors for the dot product, should you put a dot between them?
Not really. It's fine. Yeah, I think it's a good idea to distinguish it between the cross product. Even though I did it here, but it would be a great idea to put it here as well. Thanks. Mm-hmm. Okay, the dot product, that is 0 times 3, that's a 0. That's 0. Negative 8 times 1, minus 8. 0 times negative 4, that's 0. So we get negative 8. And we need the magnitude of the normal vector. All right. That is the square root of 3 squared plus 1 squared plus negative 4 squared. That's the square root of 26. Okay, so we have everything we need to find that distance, and that is the absolute value of the dot product between P and Q dotted with the normal vector n divided by the magnitude of n. That is the absolute value of -8 and the square root of 26. All right. So, well, absolute value makes it a positive. So final result, final answer, that's 8 over the square root of 26. And again, you don't have to rationalize this. It's the same from last time.
Oh.
So you don't have to rationalize the denominator. Let me just remind you about that because it's no longer that algebra class when you were first learning about radicals and when you put your final answer or MyLab, it goes like although your answer is correct, blah blah blah. No, not in this case. So MyMATLAB for Calc 3, it's more lenient about the results. Okay, and also on a quiz or on exam, you're not required to rationalize denominators. But I would be looking for how you get the vectors, how you use your notation, more like rationalizing. Okay. The last point on this, the last topic in this section is now the distance between a point and a line. Okay, so how are we going to do this? Well, let's consider a line. So we have this line given by some r of t, some vector valued function, a line that we already know how to write. Worth noting, number one, this line contains a direction vector. Contains a direction vector that I'm going to call v, simply v, okay? Now, so then we're going to have a point in the middle of nowhere, that is this point right here. Right? Let me call that point Q. In just the same way we did this setting with, what was that? With the distance between a point and the plane, we got that given point as a point Q. So that means we will need a point on the line. All right? So we want to know this distance, by the way. Because, I mean, if you think about it, there's many ways to go from point Q to the line. You might want to go like this, like that, like that, like that, all right? But actually we want the shortest distance, okay? In the same way as the distance between the point and the plane. We want the shortest distance, which is the distance that actually forms a 90-degree angle with the line, all right? With this vector valued function as a line. All right, so that's the distance d we want to know about. How are we going to get this distance? Okay. So we're going to use the same projection thing, the same projection idea. So number one. So let's come up with another point. Any point on the line, your favorite point, it doesn't matter. It could be, so we can create this vector right here. And guess what? The shadow of this yellow vector right here onto this vertical line, that's going to be our distance. What about it? Now, does that matter what point do you use? No, you can use this point right here or that point. It doesn't matter. The length of the shadow will still be exactly the same. Okay? So, let's go about and try to get a formulation for this. Well, so we need to know this distance right here, the distance from the point P to the point Q. Well, so since we are defining a vector, so that distance is going to be given by the magnitude of the vector PQ. Okay, so that's going to be the distance, right? And then, guess what? We're going to use the angle here, right? That's because, well, I'm going to derive this formula. So rather than just give you the formula and solve the problem, I like this derivation. It's a pretty cool one. So it's a good way to put together what you know from trigonometry with what you know from this class, etc. What you have learned in the previous few sections. Well, so number one, so we want to know this distance, right? We want to know this distance. We can find out about the angle between the vector and the direction and the line. We want to find the distance too. But we also know the magnitude of the vector. So how about we use trigonometry to find this vertical distance right here? So what is what trigonometric function relates this distance and sine? All right, so that means sine theta equals opposite over hypotenuse, which is the distance over the magnitude of PQ. All right. Okay. In fact, in the end we're going to eliminate the angle variable. It's in this case it's not going to matter. The angle is not going to matter in the calculation. So somehow we need to relate this to another so to speak, of another formulation involving sine. Well, let me solve for the distance d right here. So d equals to the magnitude of PQ times sine of the angle. And let's save this for later. Okay. All right. Okay. So we had another definition, another vector definition involving the sine function. That's actually the definition of the magnitude of the cross product. All right. So, well, again, the cross product between two vectors is found by evaluating the 3 by 3 determinant, right? You know how to evaluate. But there is another definition that involves the angle, that is the magnitude of, say, PQ cross with V, okay, and that equals the magnitudes of the vectors, the product of the magnitudes of the vectors times sine of the angle. Oh, okay, so here it is. So here is where we're going to solve for the to get rid of the trigonometric relation. Okay, so I'm going to use the commutative property of multiplication. You know, A times B times C, it's the same as B times A times C, right? So I'm just going to change the order of these two. The magnitude of PQ times the magnitude of the vector sine of the angle equals the cross product between PQ cross with V. All right, so now check this out. This can be replaced. Wait, I thought I changed it. This is V and this is PQ. So I'm going to put together these two, and this is equal to the distance we're looking for. PQ cross V, that equals the magnitude of the vector, the direction vector of the line, times the distance, and solve for D. That gives us magnitude of PQ cross V over the magnitude of the vector that directs the line. So that's our formula to find the distance between a point and a line. That means we need to come up with a point on the line to create that vector, and then that vector PQ cross with V, its magnitude divided by the magnitude of the direction vector. So that's going to do it. Let's see this in action with one example. Okay, so as you can see, it's a basic trigonometry derivation, a little bit. Again, one of those, if A equals B and A equals C, then A equals to C logical statements to derive or prove, if you will. Okay, so, okay. Find the distance between the point. By the way, this is the point Q. The given point is Q. We need to find what P is. Okay, so and the line given by this vector valued function. All right, again, let me draw a picture here. That's going to represent the line that we're given as a vector valued function here. And then we're going to find the distance between the point Q, which is 4, -1, 2. We want this distance, by the way. We want that distance. And what's that? We need another vector. But we need a point P on the line. That's where it gets interesting. How do we get that point? Well, in this case, we're not going to peekaboo like we did with the plane, right? Because it's a line, it's not a plane. So the line may or may not cross any of the axes, and in fact, it's a vector valued function, not a scalar that we can eliminate two variables. In fact, it's only one variable. It's a variable t. Okay, so again, worth noting. R of t contains the direction vector v equals to, what is that? 3 to 1. Where did I get these three components? These are the numbers that multiply the variable t. Okay, it's like the slope of the line, but again, there's no slope for lines in space. There's no rise over run in lines in space as we had it back in 2D, right? So this looks like a 6. Okay, t. What point are we going to choose on the line? You might ask yourself, right? Your favorite point. It doesn't matter. Again, you can choose this point right here, create a vector. You can choose this point right there, create a vector. Anyway, the shadow of whatever vector you choose, it's going to be exactly this distance, right? Or this vector right there. And it doesn't matter. But what's that point? If we get that point by evaluating the vector valued function at your favorite value of t. What would be your favorite value of t to evaluate it at? 1? Even easier? 0, right? I mean, you can evaluate r of 75,045,000 if you want. It's going to give you a vector whose shadow is going to coincide with the distance between the point and the line. But keep it simple. Okay, keep it simple. Just do r of 0. Okay, so for simplicity, the point P related to t equals 0 is the best choice. The best, easiest. Okay, so let's evaluate r of 0 then. R of 0, that equals -1 plus 3 times 0 plus 2, comma, 2 times 0 and 4 plus 0. Okay? Well, that's going to give us, number 1, this is going to give us a vector, right? -1, 0, 4. But again, we need to express this as an order triple, not as a vector. Again, keep in mind that we can simply turn this vector into an order triple because these vectors have components that are the terminal points of vectors in standard position. That is, vectors that have the origin as an initial point. So we got everything we need already, ish, right? So now we may go ahead and define the vector PQ. So, okay, P, which is what? -1, 0, 4. Okay, so terminal minus initial. 4 minus -1, careful, that's 5. -1 minus 0, that's -1. And 2 minus 4, that equals -2. What else do we need? The direction vector v. Okay, the direction vector v, which is 3, 2, 1. Okay, so we need to find the cross product between these two vectors. So PQ cross with V, and we need to set up this 3x3 determinant I, J, K, and just write the vectors as rows. That is 5, -1, -2, 3, 2, 1. Okay, so the result of doing the cross product between these two vectors, that's going to be given by 3, -11, and 13. Right? So at this point, you guys know how the cross product works, right? So I don't need to do the whole process. Okay, what else do we need? Well, from the formula, we need to find the magnitude of that vector we just found. So that is the magnitude of PQ cross with v, that equals the square root of 3 squared plus negative 11 squared plus 13 squared. And simplifying this madness in the calculator, that should give us the square root of 229 and 99. 299. Okay. What else do we need? The denominator for the formula calls for the magnitude of the direction vector of the line. That is, the magnitude of v. That's the square root of, what's that? 3 squared plus 2 squared plus 1 squared, which is going to give us the square root of 14. And in this case, notice this formula, unlike the formula for the distance between a point and a plane or two planes, does not call for an absolute value, because the formula is made by two magnitudes, and all magnitudes are always positive, right? So we're ready. D equals to magnitude PQ cross V over the magnitude of V, which is the square root of 299 over the square root of 14. And again, no need to rationalize the denominator. No need to use the quotient rule for radicals. We're good. All right? Final answer. That's the distance. Yes?
How did you initially find the points for the v vector?
Oh, the v vector, it's the coefficients of t's in the line, in the given line. Yep. All right. And I believe this is the end of the section, right? Okay, so